Hey everyone, welcome to the SEM Analytics YouTube channel, your go-to place for all SEM related analytical use cases. Today, we will be using the PuLP Python package to solve the transportation problem we discussed in our previous videos. Let's get started. The first step is to import all the necessary packages. Here we import the PuLP, Pandas and NumPy package. The second step is to create or download all the necessary input data that is given to us. In this problem, we are provided with the following two type of data. The number one is the supply rated data for the different warehouses in the network. Similarly, the total client rated data in the network. For the warehouse, we first create a list called warehouse, which captures all the different IDs of our supply nodes. And then we create a dictionary to indicate the number of pallets that each plant can supply in the network. Here, plant A, B, and C can totally supply 30, 40, and 30 pallets respectively. Please note that the IDs of the keys mentioned in this dictionary are same as your warehouse variables. We do a similar activity for the client where you have 22, 27, 23, 28 as the respective demand for C1, C2, C3 and C4. And C1, C2, C3 and C4 indicate all the different client IDs. Once we do that, the next step of data that is available with us is the cost associated with each client and warehouse combinations. So here 8 indicates $800 to supply a pallet from plant A to C1. Similarly, we have a list of lists capturing the different costs. Now let's get into the interesting part of creating the LP problem. The first step is to use the makeTicket function of the PuLP package. It's a utility provided by the PuLP package and a very interesting one as it allows you to now have indices named after the two arrays that we have or the two lists that we have that are the warehouse and clients. We need to create this because in the future when we have to reference to a particular cost associated with the route, we can simply call the make this function associated with this cost variable and indicate the indices of our interest here. Now if I want to access the 8 variable or 8 element, all that I have to do is call cost of C1 and plant A. More on that later. So this in this API, what you have to provide are the following. You need to provide the headers, the actual array which contains all the informations that can be filled into the different rows and columns, and the default values. If it's missing something, it would fill with it 0. Now that here in this use case we have clearly mentioned the different costs associated with these routes, so the cost dictionary now is equipped with all the cost data information. The first step in any LP problem is to call the LP class and define the name and the sense of the LP problem. Here we want to solve a distribution problem with the aim of minimizing the total cost. Next step is to create all the routes, which are the combinations of the warehouse and clients. We create an LP variable, which is a dictionary, and we pass in the different route information into it. Here we create it by calling the warehouse and client by passing the warehouse and client lists, and the following informations are provided. We have a lower bound of at least 0 so that it's not negative. We have no limit on the upper bound, and we want to ensure all of these variables are a category because there is no point getting a solution like 2.5 pallets, which doesn't mean anything in the practical sense. The next step is to construct the objective function. Here, what we call is very interesting, and kindly note in the previous examples, what we had basically done was associate the different cost variables or the objective coefficients individually with the different LP variables. Here, now we iterate to the route list which we created and call for the different variables and cost from the dictionary. these both are LP variables. In the case of cost, it is basically a matrix, which again is provided by the PuLP package, which allows us to reference the different elements. So let me now just comment the later part of the code and just show you how the cost and route variables look like. So I'm just gonna iterate through the different route elements and print it for your reference. So the W would call for the warehouse elements. C would definitely have the client elements. And when I now print particular cost, we would see a numerical output which comes out. And similarly, when I call the variable, uh, you would see the LP variable, which would be like route underscore warehouse and client. I'm gonna call break so that we just see one result and analyze it. So like you can see, the first element of the route list is plant A and C1. The associated cost is 8 and the decision variable is plant A C1. The reason why this is really useful is because now you can take large piece of information and codify it in this manner so that you can solve real world LP problems. One can simply down import all of this data from an Excel sheets, formulate these sort of data structures and solve for the problem. So here we have an LP sum and which is the objective function of the different objectives and different cost objectives variables and the route that we want to solve for. Similarly, we do that for the warehouse. Here, now what we encode or what we code is the two constraints, one on the supply end and one on the demand end. On the supply end, for all the client that we have and for all the warehouses that each client can supply is less than or equal to the total supply. Similarly, the minimum demand constraints is that the total sum that is given by the client and variable combinations should be greater than or equal to the demand of the client. We then write this into a LP file, solve for it, see the status, what sort of output do we get, and print the different objective and variable values, which is very similar, or this part is always similar to the other LP problems that we have. Now let's go and run this code. What we see is what we saw in the Excel sheet. The total optimal cost was 2289, and it was an optimal solution that we got. And the best routes and the different palettes are mentioned here. Now, let me just shift gears and go to the second use case that we discussed. It was a case where you had an oversupply problem, such as let's assume you have now a total supply of 110. And then when we solve for this sort of problem, we still got an optimal results where the total cost in this sort of network supply was lower than the case before. When I solve it for now, you basically have the total shipping cost as 285 because now the model is shipping a lot more from the third warehouse, which seems to be cheaper to satisfy the different client requirements. Now let's look into the third case where we had included the dummy variable, which was a case when you had less supply or you had the network having greater demand. With this, one could understand what could be the potential plant or where could you source that particular extra demand from in order to meet the different client requirements and see the lowest cost at the current network design. Here to do so, we added a new ID which represents which we call as plan D, which represents the dummy variable, and then we added a dummy cost of 000. Now when we solve for this, everything else pretty much remains the same. And now when we solve for this, we get a lower shipping cost and an optimal solution because now that you are shipping less, you definitely have a lower shipping cost. And we understand that with the current setup, there's just one node that is two. We should the 10 missing pallets in the supply nodes could be supplied from a dummy node to customer C1. And now we need to really figure out how would you really do this in a real world sense, like, probably buying it or increasing capacity at certain nodes. We have discussed a few use cases in the sensitivity video, which I recommend to see in order to understand how one can solve for these kind of cases. But that's all for today, folks. We discussed about the different cases in the transportation use case, and we used the PuLP code to solve these sort of problems. I hope the video was useful. Please subscribe to the channel for updates on future videos, and do share this video with people who might benefit from this sort of content. Until next time, thank you, bye, and happy learning.